Welcome to Brain Vision.
Okay, so in this question, we are basically finding the resonances of a shower stall. So, we're told that the dimensions of the shower stall are 86.0 centimeters by 86.0 centimeters by 210 centimeters. Now, if we convert this into meters, we, of course, get 0.860 by 0.860 by 2.10 meters. And we're told that the speed of sound in this situation, v, is 355 meters per second. And then, since we're trying to find resonances, we're concerned with frequencies. And we're told in the problem that we're supposed to assume that the frequencies of human singing are between 130 hertz and 2000 hertz. So the answers that we'll find are between 130 and 2000. So what we want to do here is we basically want to find what the fundamental frequencies are for the shower stall, and then find which overtones of those fundamentals will then be within 130 and 2000 hertz. So there's a couple things complicating this problem, making it a little bit different than usual. The first is that we are supposed to assume that the shower stall works like a pipe that is closed at both ends, and we don't have that popping up in problems very often. So, and then there's also the fact that this shower stall is three-dimensional instead of just being a linear tube. So the way that we do that is we need to analyze the shower stall with each dimension separately. So two of the dimensions are the same, but they're both 86 centimeters in two directions. So we only need to do that once, but we need to do it. But we do need to analyze the shower stall once for the 86 centimeter direction, and then once for the 210 centimeter direction. So we're basically dealing with two separate pipes. Both are closed at both ends, but one has a length L1 equal to 0.860 meters, and another one has a length L2 equal to 2.10 meters. And obviously those are not to scale. And then also, because the tubes are closed at both ends, that means that at both ends we need to have nodes rather than antinodes. So this works very similarly to a tube that's open at both ends for the math, for how the math works, but just from a physical standpoint, it is a little bit different. So what that means is that if we look at the fundamental, we're going to have a node at one end and then a node at the other, and then an antinode in the middle. For the first harmonic, we'll have to add one more node in the middle, so it's going to look like this. And then for the next harmonic, we'll have to add one more node, so we have something like this. And I'm putting them on the different tubes just to make things a little less cluttered. And then for the next one above that, we will have this kind of look. So this is just helpful for visualizing it, but the end result is that the possible relationships between the length of our tube, in this case the dimension of the shower stall, and the wavelengths of resonant frequencies are going to be L is equal to lambda over 2, lambda, 3 lambda over 2, 2 lambda, and so on. But really the important takeaway here is that each higher frequency is just an integer multiple of the fundamental. So the first harmonic, lambda, is just going to be twice the fundamental. This one is 3 times, this one is 4 times, the next one is 5 times, etc., etc. So once we find the fundamental frequency for each dimension, we can just multiply that by each integer value to find all the possible harmonics. And we're just finding what fundamentals and what harmonics for each of the dimensions lie between 130 hertz and 2000 hertz. So it's a little bit more complicated than some of the other problems, and we end up with a lot of answers. So I'm going to do this one tube at a time, one set of dimensions at a time, and I will give all the answers that are related to that dimension, and then I will repeat it for the second one. So this is kind of a two-part problem. So the first one is the dimension of 0.86 meters. So the way that we do that, the fundamental frequency, we'll call that F1. The fundamental frequency for the length of 86 centimeters is going to be equal to the speed of sound divided by the wavelength of the corresponding wave. So we'll call that lambda 1. And we've said that the fundamental is going to be related like with this relationship. So L is equal to lambda over 2. We can rearrange that to say that lambda is equal to 2L. So then we can substitute that into our formula. So then V is equal to 2, or V divided by 2L1 is equal to our fundamental for the dimension of 86 centimeters. So then we can go ahead and plug in values. So V is 355 meters per second in this problem, a little different from normal, and then that's divided by 2 times 0.860 meters. And you plug that into your calculator, and you'll get that our fundamental in this direction is 206 hertz. So that is our first fundamental. And then from here, we are just trying to find all the harmonics of this fundamental that lie in the frequency range of 130 hertz and 2000 hertz. So all you do here is you just multiply 206 by 2, 206 times 3, 206 times 4, etc., until you find a number that is greater than 2000, because that is out of the range of frequencies that we're looking for. And so I will let you do all of that multiplication on your own. If you want to try that on your own before I just give out the answers, go ahead and just pause the video now. I'm going to go ahead and just list off the answers. So that means that our answers for this dimension are 206 hertz, 413 hertz, because of course there are some decimals after. You'll notice that that isn't actually 206 times 2, but there are some decimals after the 206, but we only have 3 sig figs. So we do cut it off, but so there is some rounding here. So after 413 hertz, there is 619 hertz. Then there is 826. 1030. 1240. 1440. 1600, 50, 1860, and I believe that's the last one. All right, yep, that's the last one for this dimension. So these are all of our answers just for the dimension of 86 centimeters. So now we just do the same thing, but this time we're dealing with the length of 210 centimeters. So then we have F2 is equal to V divided by lambda 2 And we have the same relationship as before between lambda and L, so we can go ahead and just substitute that in the same way. So V divided by L2, or V divided by 2 times L2. And L2, of course, is 2.1 meters. So we have 355 meters per second divided by 2 times 2.10. And then that'll give us a fundamental of 84.5 hertz in this direction. Now we're looking for answers between 130 hertz and 2000 hertz. So this answer actually is not, or this result is actually not included in our answer. But we'll start doing multiples of that, and all of those multiples will then be in that range. So 84.5 is our fundamental for this direction, but it is not part of our answers. So then all the harmonic, I'll do the same thing as I did before. I'll start listing off all of the answers for this dimension. If you want to find them out yourself, go ahead and just pause the video. And then I will go into that. We're just doing it the same way as we did before, just multiplying 84.5 by integer values until we get above 2000 hertz. So then the answers for this dimension are 169 hertz, 254, 338, 423, 507, 592, 676, 761, 845, 930, 1010, 1100, 1180, 1270, 1350, 1440, which incidentally we had in the first part as well, 1520, 1610, 1690, 1780, 1860, and last but not least, 1940 hertz. And so these are all of our answers for this part. But yeah, so we have a lot of different individual answers here. But the basic formula for each one is for the dimension of 86.0 centimeters. The formula is 206 times n, where n is just an integer value starting at 1. And just make sure that those values are between 130 hertz and 2000 hertz. And for the dimension of the 210 centimeters, the answers are 84.5 times n. And again, integer values starting at 1. However, and then just make sure, again, that those values are between 130 hertz and 2000 hertz. Because 84.5 is less than 130, it's not in our range for answers. So you won't include that in your final answers. And yeah, that is how you do this problem.